All right, for this notes, this is the last standard of this unit. We're going to be talking about mass and weight, but before we do that, I want to go over all of the forces that we have learned in the past. So this is a good review for you to keep thinking about what is a force. So force is a push or a pull. And the force is always measured in newtons. From there, we can split all of these forces into different categories. And you already wrote these on your note card, but I want you to write these down. We're not going to write all of it. I'm just going to give you I'm just going to give you the symbol. So F, which is friction, is when there is two surfaces and motion. So the requirement for this one is that there's two surfaces and motion. And I told you that a type of force that's like friction is air. So F air or drag is when one of the surfaces is molecules of air. Other normal or other forces that we have talked about are normal force, so Fn, and this is when there's a surface. We have Ft, which is tension, and this is when we have rope, string, or wire. And we also have applied force. And the applied force is when there's a person, animal, or object that is pushing or pulling, or object. And the last one that is actually on the top of your list on the other on the note card is gravity. And gravitational force, you wrote on your note card, that is also known as weight. So gravitational force is the planet pushing you down on Earth, which is actually the weight that an object is experiencing. So this gets us to the difference between mass and force. Mass, not mass versus force, mass versus weight. Mass is the amount of matter in an object. The amount of matter making up an object. You are made of matter, so you matter. And then you'll see that mass here. And then you'll, if you look at the picture, you could see the atoms. So these are the different atoms that make mass. Weight is a force, and that's why there's an arrow here as he's on this planet, and force is pushing him down. This force of gravity is pushing him down. And that is because weight is the force of the planet pushing you down. So the force of gravity pushing you down. Right, and it's going to be different for every planet. So on Earth, the gravitational acceleration is 9.8 meters per second squared. This is for Earth. The gravitational acceleration for Mars, on the other hand, is actually a lot smaller at 3.7 meters per second squared. And the gravitational acceleration of the Moon is 1.6 meters per second squared. The size of the planet takes effect into the acceleration, and at one point we actually had to calculate the gravitational acceleration for each of these planets depending on the radius. This was once calculated very simply using an equation and knowing the radius of the Earth. We're not going to get into those equations. I don't even know if Honors does them anymore, but they're equations that we're not going to worry about at this point. But I am going to give you the equation that you're going to use to solve for FG. So FG equals mg. And I'm going to create a little tree for myself to remind myself that this Fg is the weight and that the unit for this is newtons. M is still the mass. Mass is always in kilograms. And G is the gravitational acceleration of the planet. And I'm going to give you a very important side note. The weight is going to change depending on the planet. However, mass, the amount of matter, never changes. Okay, so would not be affected by the planet. Not affected by a planet. That's the big key thing to know. This number is going to be the same. If you are, this guy is 60 kilograms as his mass, and he goes to Mars, he's still going to be 60 kilograms. If he goes to the moon, he's still going to be 60 kilograms. This amount is never going to change.